Okay, hello, welcome to the class again. So this lecture is going to be about the fundamentals of image formation. So any camera creates an image. The image I of xy is a measure of how much light is captured at pixel xy. We are interested in two questions. First, where does a point xyz in the world get imaged, and what is the brightness of the resulting point xy? So in this lecture, we'll try to get a handle on the first question, which is where does a point xyz in the world get imaged? So this is the so-called pinhole camera model. We ignore lenses and such for the time being. We imagine that all the light on the imaging surface, which is at the back here, comes through the pinhole of the camera, and this object for which we see this point P is imaged to the point P prime. And let's take note of the coordinate systems here. The coordinate system here is located at the pinhole of the camera, and we have the x, y, and z axes in the world. The z axis is what's called the optical axis of the camera. And then we have the x and y axes. Notice that in computer vision we very often follow this coordinate system where y is up and z is away from the camera. This is distinct from the notation usually used in physics where z is in the direction of the gravity vector. Okay, let's stay with this notation. We also have a coordinate system on the image plane, and that is indicated here by little x and little y. So the little x and little y notation corresponds to the coordinates on the image plane of the camera. So our goal is going to be to figure out the relationship between the coordinates of the point P in the three-dimensional world and its coordinates in the projection. And the basic equation is given by little x is minus fx upon z and little y is minus fy upon z. So okay, so let's derive this equation. How do we do that? So we're going to prove a special case first, and this is for the special case of a point P in the YZ plane. So let's go back to the image so you can remember what's going on here. We're going to consider the point P, but we'll consider a special case when it lies in the YZ plane. We're going to draw out the optical axis, and we are also going to show the projection of P in the image plane. So that's P, and this here is the projection of P, little p. And what are these distances? This distance here is going to be z. This distance here is going to be f. This height here is going to be given by uppercase Y, and this height here is going to be given by y, little y, but actually it is going to be minus y because the coordinate system, in the coordinate system the y-axis points upwards. Let's go back so you can see that I've drawn this correctly. So if you look at this slide, it becomes clear what I'm trying to do. I'm trying to draw the coordinates, but since the y-axis points up, a distance going down should be marked as minus y. Okay, so we are back to this equation, and now we have a fairly easy job. We use similar triangles. The two triangles here are similar to each other. So therefore, what we can say is f divided by minus y is equal to z divided by uppercase y. And this implies that y equals minus f uppercase Y divided by z. Okay. Now this was for the special case when the point P lies in the YZ plane. But really this is true even if the point P is not in the YZ plane. And the way you can convince yourself of that is that all we have to do is to consider the projection of P on the YZ plane, and then this relationship will be true. So we have derived this equation for the projection of the Y coordinate, and by similar reasoning we can expect that we will get a relation of the type x equals minus fx upon z. So this just states this, and now I've written out this equation in sort of nice mathematical notation. So notice a few things here. So there are some conventions here, which is that the lowercase quantities are used to correspond to variables on the image plane, and uppercase variables are used for points which are in the scene, in the three-dimensional scene. So if you notice, look at these equations, there is one annoying property of these equations, which is that there are these minus signs. The little x is minus fx upon z, little y is minus fy upon z. Now what these minus signs correspond to is that the image is inverted. The image is inverted both upside down as well as left to right. And this is something you can find annoying, but this is actually true of projection of images even in the retina. And in fact, the diagram that I have is from Descartes' La dioptrique. So we know this. The image is in fact actually inverted. So this caused many people a lot of consternation back at once upon a time, even people such as Leonardo da Vinci. And they proposed various designs of what could happen in the eye so as to avoid this inversion or to do the recorrection. But this is really not so much of a big deal. The point is that the brain can interpret the image the right way. And for a camera, its life is particularly easy because software can simply flip the image top down and right left. And after we apply this trick, what we get is much nicer looking equations, which is little x equals f uppercase x divided by z, little y is f times uppercase y divided by z. So we've got rid of the issue of lateral inversion and top-down flipping. Good. So now we are ready to start to understand the mathematics of perspective projection. And for this I have picked this drawing. It's actually a drawing, not an image, but since the drawing is trying to be accurate about perspective, we can consider this. So on this, in this image, which let's say corresponds to a camera taking a picture of some telephone poles and some cacti and a road and some grass and so forth. Let's try to look for some phenomena which arise due to perspective projection. So here's one. Parallel lines in the image converge to a vanishing point. So the parallel lines that I have considered here are the feet of the various poles and the tops of the poles. The tops of the poles constitute one line, the feet of the poles correspond to another lines, and the two sides of the road. And all of these appear to converge to a vanishing point. So note that this is a phenomenon of perspective. The lines themselves do not meet in three-dimensional space. They are parallel to each other, but their projections in the image appear to meet. So can we explain this? Okay, here's another observation. So we have that nearer objects are lower in the image. So here I have denoted by y1, y2, y3 the y coordinates of the feet of these poles, and you'll notice that the nearer pole has a foot y1 which is closer, which is lower in the image. Nearer objects look bigger. This again should not be a surprise. So let's take up some of these properties and try to prove them mathematically. So first let's take up this property that parallel lines converge to a vanishing point. How will we go about proving this? So let there be a point A and a direction vector D in three-dimensional space. And what we'll do now is to write down the equation of a point on this line. And what can we say about that? We can write the equation of a general point on this line as, here are the three coordinates x, y, and z, and these are equal to a sub x, a sub y, a sub z plus lambda times d sub x, d sub y, and d sub z. So x here lambda, so let me draw a picture here. So suppose we have some point A, and then we consider some line going through it, and the direction of this line is D, and so we'll get a point here which is A plus D, and then there might be a point here which is A plus 2D, and there might be a point here which is A minus D, and so on. So the general way to think about it is that we have this parameter lambda, and lambda ranges between it can go to infinity in one direction, or it can go to minus infinity to consider points on the other side. Okay, so by varying lambda we get different points on this line. So let's now figure out the projection of this point. How do we do that? So let's look at the x coordinate. So we have this equation, little x equals f x upon z. So if we want to apply this, we have f times what's the x coordinate? It's going to be a sub x plus lambda d sub x divided by what is the z coordinate? It's going to be a sub z plus lambda d sub z. Is that clear? Good. So now what we can do is we want to figure out what happens to this coordinate of this projected point as the line goes to infinity in three-dimensional space. So how do we find that? Well, let's consider lambda going to infinity. So then what's going to happen? What happens to this expression? So in this expression, in the expression for x, essentially the dominant term will now become lambda dx divided by lambda dz, which will give you f d sub x upon d sub z. Okay. Now the interesting thing here is that this expression does not depend on A. So therefore, if we have a family of parallel lines, they all will have the same direction D, but they will go through different points A, but the projection coordinate X does not depend on that. So in general, so what we have shown is the coordinates of the projection are f d sub x upon d sub z for the x coordinate, and we, by analogy, I haven't, and by doing the same process, for y coordinate, we get f d sub y upon d sub z for the y coordinate. And thus f d sub x upon d sub z, comma, f d sub y upon d sub z are the coordinates of the vanishing point of this family of lines. Okay, let's take a break here.